You know, there is the widespread conviction that in order for a brain state to be conscious, it has to be coherent in some sense. The different modalities have to stand in certain relationships. So I published that idea in 1997 under that name, the coherence definition of consciousness. And then I had to learn, somebody told me, Nancy Canwisher actually, oh, that reminds me of Bernard Baars' ideas. Okay, he was earlier. And then came along a while later, Giulio Tononi. Bernard Baars' idea of coordination is that all the modalities look at, write to and read from a workspace, as we heard from Lenore yesterday. The idea of Giulio Tononi is, as I understood it when I first encountered it, is that the volume of the state space of a given modality is enormously reduced by the coupling to the other modalities. So if you cut the lines between them, then the volume of state space would be increased. It's a kind of informational coupling. I think all this talk about coherence, or whatever you call it, and for that matter, all talk about consciousness is provisional and preliminary before we come to terms with a particular question, and that is the question about the structure of brain states. Together with answers to these other questions, how do the parts of a brain state relate to each other? I mean, that's the basis for coherence or correspondences between different parts of a brain state. How do they relate to the environment, of course? How do states transition into each other? What generates the flow of states? How are they formed? How they are on the short time scale? How are they formed? What is the structure of the common substrate? They all live on the same physical substrate. What is the structure of that? And how does that substrate develop in self-organization, genetic programming, and so on? Now, let me express a very fundamental assumption here, which is that brain states are dynamical attractors. There are many theories, certainly the deep learning theories, which deviate from that. They are based on feed-forward between consecutive stages of operation. What I claim is basic to the brain is that a given state is a dynamical attractor held together by lateral connections in distinction to feed-forward connections. That puts you into a very different realm of theory. So I think, just to have a number, a state is characterized by there being a small fraction of all neurons being active, and I think of something like 10 to the minus 4, and they support each other. So in what I am going to talk about, I make a difference between things that go on within areas and things that go on between areas. As we know, different areas might be organized in a hierarchy, as Velleman and Van Essen in their famous paper express. So let me first talk about what goes on within a state. So the idea is you have within a typical area, you have something like 10 to the 8 neurons. And in a well-organized state, only 10 to the 4th neurons are actually active. And those neurons that are active are all supported by excitatory connections from other active neurons. Forgive me for this figure here. I just grabbed it from the internet. All the different symbols here just mean neurons. Okay, so what does it mean for a neuron to be supported by others? So the idea is, here is this is you, a neuron, and you can only maintain yourself in a state if you have a minimal number of supporters that excite you. And according to some old computation by my friend Moshe Abiles, it needs the pileup of at least 10 EPSPs to bring a neuron near to its firing threshold. So to have a safety factor, I'm assuming here you have dozens of, you need in order to be reliably active in a state, you need dozens of supporters. So that is a very stringent constraint on what is acceptable as a state, because number one, it is very non-trivial for a neuron which has 10 to the 4 incoming connections. It's very non-trivial to find that many friends in a state. If you assume that the fraction of neurons that are active is 10 to the -4, then in a randomly connected network, the expected number of friends is 1. And this is very far from 1. And then, of course, all your friends need their support. They cannot be active if they don't have their support. So this condition of a state being viable, being admissible in the conscious state, to be composed of neurons that all have minimal support is a very stringent one. So let me talk in net fragments. A minimal net fragment is you as a neuron and your friends. That is a minimal net fragment. And you can go to a second generation. You also include all those friends of your friends. And you can go to a third generation and so on, assuming that these fragments get bigger and bigger, which is some condition on the structure of the whole network. Now, these fragments form a hierarchy of feature detectors, and I would like to compare them, talking about a multi-layer perceptron, to high-level feature detectors, which there are represented by individual neurons. Here the idea is that you, your friends, and the friends of your friends together represent some kind of pattern, and that is a feature detector. And so these feature detectors put you in a very different kind of dynamics, because they are not independent of each other. The different feature detectors overlap neuron-wise, so they form a continuum. Okay, so let me just say there is a vast multiplicity of fragments. If you look at a particular spot in your small region, patch in your cortical area, there are thousands of minimal fragments in each of them. Each neuron is part of hundreds of minimal fragments. You know, it needs a few dozen connections to be activated, but it has 10 to the 4th connections. So there is space for a given neuron to be part of many minimal fragments. And each minimal fragment overlaps with others. So let me talk about this overlap. And I would like to compare that to jigsaw puzzles. In a jigsaw puzzle, these bindings, these correspondences between neighboring fragments are unique. You have to find the one correct piece in a jigsaw puzzle to fill that space. You could, of course, think of a more ambiguous kind of game, like Lego, where the condition is much looser. You are only restricted by steric hindrance and so on. And what I claim is we are here in the middle, where each piece of the jigsaw puzzle, you know, the net fragment, can have, is ambiguous as to which other pieces it would fit. Now, in a jigsaw puzzle, you have to move the pieces to get them into place. Here, you can't move those fragments. There are lots of fragments in a given space, and the question is which of these fragments is activated. That's the mechanism. And as I said before, there is a very stringent condition of what fragments can live together, because they have to be consistent. If in an ordinary jigsaw puzzle you make a mistake to put to put here a piece that doesn't belong there, then you have created surfaces which will never find another partner. So the thing cannot be consistently continued. Nets, organized, active nets have to be consistent in this sense. Let me remark, as we were invited to talk about mathematics here, that I realized nets, organized nets as described, are topological spaces. They conform to Hausdorff's definition by neighborhoods. There are a few axioms which are fulfilled here. And the neighborhoods are these generations of net fragments. So you are a neuron, and you are embedded in the first, second, third generation, and so on of net fragments, and they conform to Hausdorff's axioms. Now, if that is true, then one can think of, and now I come to the interaction between different areas, you can think of homeomorphic projections between nets. So assume you have a net active in this area here, which has a certain structure in terms of labels on the networks. Individual neurons can be distinct, like texture-sensitive elements, for instance. So you can have a large number of different nets active in a given area, and they are all distinct to each other. But you can create a situation where a net in this, in this position here, I hope you can see my pointer. Let me try to, should be able to. Well, if you have a given net in this area with a given structure, one can imagine to have a homeomorphic net in another area, and you then have the task of finding the correspondence. And what I claim is that you have multiplicities of fibers between areas from which you can select fibers such that these homeomorphic mappings are established. So this is a step I have great difficulties selling in my scientific environment. These projections between areas are highly dynamic. They switch as quickly as, for instance, an object moves on your retina, in order to keep the correspondence between a moving image in your primary visual cortex and a model of that, invariant model of that object. You may shrink from this idea. I've worked out the details in terms of numbers, in terms of dynamics, in terms of development of self-organization of these networks. Believe me, it works. So from one split second to the next, the mapping can jump around. This net here moves, as for instance, representing the image of an object, and it reconnects to an invariant representation of that. Usually that goes through a number of intermediate steps in order to reduce the number of required connections. Now, let me take a slightly more global view. Here you have the external world, the scene in which you are, in which you are. Here you would like to construct an internal representation of that scene. And the difficulty is that you see this scene only through sensory modalities like seeing, hearing, touch, for instance, which are very fickle. When you move around, then the representation, the reflection of the external scene in your modalities changes very profoundly. And so you have to compensate for that by having rapidly changing projections inside the system. And this, the motor control system is, of course, responsible for your movements, is responsible for those changes. And this process is helped a lot by what they call reafference principle, by signals that tell the perceptual apparatus what the movement was that you have just performed. So I introduce a new element. which goes back to an idea by Charles Anderson, who published that very much with several times with David van Essen and Bruno Olshausen, control units. Those are units that can gate those projection fibers. And so you can switch in and out whole bundles of projection fibers in a few milliseconds. That's a very important aspect. And as, for instance, envision this object here, this image can move in 2 dimensions. They form a 2-dimensional array of units in order to implement this, these dynamic projections. So in a more global view, the organized state in the brain is defined by individual areas of the brain falling into a structured net, and each unit, each area holds an essentially infinite number of potential nets, and the whole thing is only consistent if also the projections between them are consistent between the different nets, and you know, you need these commutation relations in order for the whole thing to be consistent. And I would claim, Lenore, that once the system has fallen into one of those consistent states, that's your workspace. It's spread out over the whole thing, but that is your workspace. And I will come to what it means to project down to the different subsystems actually in the next slide, which talks about the actual activation of those nets. They are miraculous things because they have to be consistent, which is a very non-trivial condition. So how are they produced? Here is, you are again in one area. Here you have the 10 to the 8 neurons. Some of them, say 1% of them, get afferent input from the senses or from another area. That's the projection down. That's the input that they get. So they only 1% of all of them are allowed to fire for a brief moment. But then in a second step, all those drop out that don't have sufficient support, reducing that to 1% of the 1%. And I would love to lead an extensive discussion in which I claim that this collapse here is what induces the community here in Oxford to take the measurement collapse of quantum systems so seriously. That is analogous to the measurement collapse of a quantum computer. It's an analogy. It's, I don't claim this as the computational power of a quantum computer. It can only solve a subset of the problems. But that's the analogy, and that is, I think that's a very important point. Now, let me talk about the establishment of the connections. I earlier said in a randomly connected network, you don't get consistent nets, so you have to reorganize the maybe originally random connectivity. Formation of nets within an area. Formation of you are this neuron, you want to find your friends. Now, the patterns of afferent fibers are complex, and no two of those patterns are alike. They never repeat, but there may be subsets of those afferent fiber projections that do repeat. And you as a neuron that has a space of potentially 1 million connections, you only have 10,000, but each of these connections can be altered by small movements of axonal tips. So you can potentially connect to 1 million neurons, and so you may be sensitive to the appearance, repeated appearance of a pattern of first stage neuron activations, and then you can strengthen your connections. So the process of self-organization of these connections is an expectation maximization process in which a pattern, an incoming pattern, decides which neurons are to be activated, and those neurons that are activated modify their connections to adapt them a little more to the current incoming pattern. Okay? So that is a process of network self-organization. So you have emerging attractor nets, which the connections, the current connections, have an influence on the statistics of neural activity, and the statistics of neural activity plastically deforms the connections until the two conform to each other. So these form attractor nets, which conform to two constraints. One is sparsity. I haven't named that yet. I said you need a minimal number of connections, but okay. But you also, an individual neuron doesn't accept more than say twice the number of minimal connections. And another kind of self-organization of connections is those homeomorphic projections. I've spent maybe 2 decades of my life in understanding the establishment of those. I don't have the time to go into detail here. So the brain is dominated in this second step process to brain-spanning consistent nets, which locally are nets in an area, and globally are networks of projections between them. So I think this is the basis, the playground for category theory. Each of these net attractors is active for just a moment, and the net is restless. It changes on a fast time scale of, say, 100 or 200 milliseconds. That's what they call the psychological moment. Now, I have talked enough about the substrate of nets, and I would like to sort of summarize the gist of this whole theory by this figure here. When you look at that figure, you see a face, of course, I suppose, unless you are have a very unusual visual system. How come you see a face? There are lots of details in this thing which you can concentrate on if you put your mind to it. But what appeared first to you was the global shape of this thing. Now, the global shape can only be established if on the basis of particular selection of local net fragments, as I call them. So what this demonstrates, this is the Gestalt phenomenon, what this demonstrates is that the nets that form have a tendency to look for the most global, globally ordered net. You need the collaboration of several areas, because you need high-level areas so that your net fragments span a larger part of the image. And I think this already, this little demonstration already contains the conundrum of consciousness, because the parts here can only be interpreted by knowing the whole, and the whole can only be established on the basis of parts. So the whole thing is, as I say here, so consciousness is a holistic phenomenon that I think makes it so mysterious. There is, so I asked the question in the title, what is coherence? Coherence, you have coherence if there is a consistent composite of net fragments and homeomorphic mappings that form a consistent map. Consciousness is a holistic phenomenon. Thank you.